Hey everyone, and welcome. Today we're going to get our heads around a concept that is, no joke, everywhere in mathematics, the sequence. And you might not even realize it, but this pretty simple idea is actually the bedrock for some of the biggest topics in math, especially that powerhouse we call calculus. So I've got a question for you. What could possibly connect the way a deer population grows, the interest building up in your bank account, and the deep, fundamental ideas of calculus? I mean, they seem totally unrelated, right? Well, believe it or not, they all speak the same hidden language, and that language is sequences. Let's dive in. All right, first things first, let's start at the very beginning. What exactly is a sequence? Well, you can think of them as the basic Lego bricks that build up all sorts of amazing and complex mathematical patterns. Okay, don't let the formal definition up there scare you. When you boil it all down, a sequence is really just an ordered list of numbers. That's it. There's a first number, a second, a third, and on and on. And that little n you see, the one in a sub n, it's just a tag, like a ticket number, telling you that term's exact spot in the line. Now, what's really cool is that there are two main ways to cook up a sequence. Think of the explicit formula on the left as a GPS. You want to know the 500th term? No problem. Just plug in 500 and bam, you're there instantly. The recursive formula on the right, though, is more like giving directions step by step. It tells you how to find the next term based on the one you're on right now. But here's the wild part. Look, two totally different recipes, but they bake the exact same cake. The sequence 3, 5, 7, 9, and so on. So listing out the first few numbers is one thing, right? We can do that. But here's the question that really opens up a whole new level of math. If this list just keeps going and going and going forever, where is it actually heading? And that very question leads us to one of the most powerful ideas in all of mathematics, the limit. This is the end game. We're trying to figure out the sequence's ultimate destination. Here's the main idea in a nutshell. If the numbers in your sequence start getting cozy and inching closer and closer to one single value, we say it converges. It's settling down. But if the numbers just go wild, maybe they shoot off to infinity or just bounce around forever without ever settling, then we say the sequence diverges. All right, enough with the theory. Let's get our hands dirty and see this in action. We're going to try and find the limit of this sequence right here. A sub n equals n divided by n plus 1. Now, we could just plug in bigger and bigger numbers for n, like 100, then 1,000, then 1,000,000, but that's the slow way. There's a much slicker trick. First, you look at the denominator and find the biggest power of n. In this case, it's just n. Next, you divide every single piece of the fraction by that n. And then, here's the magic. We ask, what happens as n gets ridiculously huge? Well, any little piece that looks like 1 over n is going to get teeny tiny, so small that it basically becomes 0. And check it out. After we do that division trick, our kind of clunky fraction cleans up beautifully. We're now just looking at the limit of 1 over 1 plus 1 over n, so much simpler. And now for the big finish. Remember our magic trick? As n rockets towards infinity, that little 1 over n part just, poof, it vanishes. It becomes 0. So what are we left with? 1 divided by 1 plus 0, which is just 1. This sequence converges to 1. And that just makes sense, right? Think about the terms, 1/2, 2/3, 3/4, 99 over 100. You can feel them getting closer and closer to 1. So that last sequence was nice and well-behaved. It found a destination. But not all sequences play by the rules. What happens when a sequence just refuses to settle down? Let's take a look at a classic troublemaker. Let's just write out the first few terms and see what happens. The first term is -1. The second term is +1. Third term, back to -1. Fourth, +1. I think you see the pattern here. It's just going to flip-flop between -1 and +1 forever. And that, my friends, is a perfect example of divergence. It never commits. It never settles on a single number. Because it's always bouncing back and forth, we say the sequence diverges. It has no limit, end of story. Okay, let's hit pause for a second and talk about a few common tripwires. Seriously, knowing these little traps ahead of time is one of the best ways to get really good at this stuff. Here are the top 3. First, and this is a big one, don't mix up sequences and series. A sequence is just a list of numbers. A series is when you add up that list. Totally different things. Second, remember our little bouncy sequence that went from -1 to 1? It was bounded. It was trapped in a little box. but it still diverged. So just because a sequence is bounded doesn't automatically mean it converges. And finally, always check the starting index. Does the pattern start at n equals 0 or n equals 1? It might seem like a small detail, but trust me, it can change everything. So I can probably hear you thinking, okay, this is kind of neat, but when am I ever going to use this? Well, it turns out this abstract idea shows up in some really powerful and surprising places. Let's go to biology. Ecologists actually use sequences all the time to model how a population of animals, like fish in a lake or rabbits in a field, might change from one year to the next. It helps them predict whether the population is going to boom or bust. And this table shows you exactly how. It all boils down to that little r, the growth rate. If r is bigger than 1, the sequence diverges. It shoots off to infinity, meaning the population explodes. But if r is less than 1, the sequence converges to 0, meaning the population is heading for extinction. The limit basically acts like a crystal ball, predicting the future fate of that population. So here's the real takeaway, the big idea. Sequences are our first and most fundamental tool for modeling anything that changes in discrete steps. Whether that's the change in a population from year to year, or the change in your bank account month to month, it all starts with this simple, powerful idea of an ordered list. So I'll leave you with a challenge. Now that you know what you're looking for, start noticing the world around you. Could the height of a bouncing ball on each bounce be a sequence converging to 0? What about the frets on a guitar? The world is absolutely full of these hidden patterns. What will you find?